Greetings out there in YouTube land. I've been asked several times to make a video about how to bias amplifiers, and I've been hesitant for two reasons. Number one, it's a complex issue, and number two, it's a dangerous procedure. But I thought today I might as well give it a try and also provide you with all sorts of little tricks and safety measures that will keep you safe while you perform this procedure. First, let's cover some basic topics. What is tube biasing? What is the criteria or the values in the tube that you have to measure to do it? And how does it affect the performance of the amplifier? First, let's start off with how tubes work. A very basic understanding here with this very simple diagram of a triode tube that has the three parts we need to understand: the cathode, the grid, and the plate. Now, the way output tubes work is a heater down here receives usually 6 volts of alternating current. It heats up and glows like a light bulb, heats up the cathode. The cathode then emits electrons that pass through the grid and go to the positively charged plate. Now, the rate of flow of the electrons from the cathode to the plate, just like water flowing, is the plate current. The amount of charge on the plate, the positive charge, is called the plate voltage. And those are the two values that we need to know to properly bias the tube. Also, I might add that there's 2 ways to control the flow of current from the cathode to the plate. Number one, we can go in and modify the wiring to the cathode, or we can adjust the grid voltage. So 2 ways to regulate plate current. We can go to the cathode to do it, or we can go to the grid to do it. Now, different amplifiers use different methods. Generally, single-ended amps, that means one output tube, like the Fender Champ, use the cathode method, and they attach a bias resistor to the cathode. Now, other amps, usually ones that have push-pull output tubes and much higher wattage amps, will use the grid control method. I'm not going to go into that in this video. Today, we're just going to discuss cathode-biased single-ended amplifiers, but that will give you a basis of knowledge that we can apply in future videos to the ways to bias the more complex and higher wattage amps. Now, the first thing we need to discuss is what tube biasing really is. Now, some people feel that just simply adjusting the plate current is all you need to do. You'll look up in a tube handbook what an appropriate plate current is for the 6V6 tube. We'll set that and be done. It's way too superficial because there's a second value here that has to be taken into consideration, and that's plate voltage. So most people, I think, consider tube biasing to be adjusting the plate dissipation of the tube. Now, that's a name that might put some of you off, but what it means is how much heat is the tube releasing? How many watts of heat? How hot is the tube? Now, the 2 things you need to know will be plate current and plate voltage. And then to calculate plate dissipation, all we're going to do is multiply the plate current in milliamps times the plate voltage in volts. And I'm going to demonstrate exactly how this can be done safely. And another issue that comes up is, why do we care? Why do we bother to adjust the bias of the output tubes? Well, first off, if they're too hot, they're not going to last long, and these tubes are not cheap. But also it affects the tone of the amp. It affects the tone itself, and it also affects something that's very important to us, and that is headroom. Now let's look up here. This is going to be like Goldilocks and the 3 Bears. If we adjust our bias so that it's too hot, we have too much headroom. We would have to turn up. Now, as you turn up the volume, these peaks and troughs will increase in height and depth. If we turn the volume up a lot, we will probably never reach the point here of clipping and distortion. So this is too hot. This might be okay if you wanted miles of really clean headroom, but to most people, this is biased too hot. Now, if you bias too cold, you bring in the limits of clipping too close here to the center line so that even at normal volumes, you're clipping, which means that playing at like bedroom volume, you're going to end up with a distorted output. And the sound will not be good. So this is a reason that some amps tend to have distortion at low volume. The output tubes are biased too cold. Now, just right is that we have a sufficient amount of headroom to allow us to operate the amp at a moderate volume and have a good clean output. And then if we want distortion, we can turn the volume up to 7 or 8 and reach the point of clipping here and distortion so that we can have the best of both worlds. Clean output at lower volume and a nice level of distortion at upper volume. Now, looking at this diagram, let's see how we're going to adjust the cathode bias of this output triode tube. Now, most output tubes are not triodes, they're pentodes. They'll have 2 more screens up here, but we don't need to worry about that to get an understanding of how to do this procedure. The way we're going to modify this tube bias is we're going to alter the value of this bias resistor. Every cathode biased amp has a resistor connected between the cathode and ground. Now, if we increase the value of the resistor, we'll reduce the plate current. It's just like we turn down the faucet. So the higher the resistance of the cathode bias resistor, the lower goes the plate current and the lower goes the tube bias. If we reduce the resistance value of that cathode bias resistor, it's like we open the faucet and more current flows and the bias goes up, as well as the plate dissipation and the headroom. Now, the amplifier I've chosen for this demonstration is a Gretsch 6150 amp. It's made by Valco back around 1960. And it has the single 6V6 output tube right here. And we see that the cathode, which looks sort of like a squared off wide horseshoe, comes out here at pin 8, and between pin 8 and ground there is a 330 ohm 1 watt carbon resistor. We're going to calculate the plate dissipation of this 6V6, and to do so then we need to know the plate current and we need to know the plate voltage. Now, measuring plate current directly would involve us cutting this wire right here and putting an ammeter in series with the output transformer in the tube, which is not a real healthy thing to do. So we're going to measure the plate current of this 6V6 indirectly using Ohm's law. Ohm's law tells us if we know what this resistance is, and we know what the voltage drop across the resistance is, we can calculate what the flow of current is through the tube. Don't worry if that doesn't make sense to you. It doesn't matter. You can still perform this procedure and get good results without fully understanding Ohm's law or anything like it, as long as you just follow some very simple steps. Okay, before we continue then, let's have a brief review of how we're going to bias this 6V6 output tube. In other words, how are we going to accurately calculate its plate dissipation? Number 1, we need to know the exact value of the cathode bias resistor. It will not be exactly what the schematic says. It'll probably be a little higher because over time, carbon resistors tend to increase in resistance. Number 2, we need to accurately measure the voltage drop across the resistor. If you don't know what voltage drop is, that doesn't matter. I'll show you how to measure it, and that's all that you'll need to do. Number 3, we'll need to accurately measure the plate voltage up here on the plate of the 6V6. With those 3 values, we will accurately calculate then what the plate dissipation value is for this tube, and we will know its bias. Also, we need to know what a good normal value is for a 6V6 for plate dissipation. And most people say the maximum comfortable limit is around 12 watts. Keep that in mind as we're doing the procedure, and let's see if we come out anywhere near 12 watts. If we're way over it, we're biased way too high. If we're below it by too much, we're biased too cold. We really need to be somewhere in the 12 watt range. Now, during the procedure, I'm going to tell you different safety techniques. But one that I don't discuss that I'm going to tell you now is when we're working in the chassis, only use one hand. Apply your test leads and remove your test leads with one hand. If you complete a circuit through both of your hands, the current will flow through your heart. And we've all seen on ER and all when they apply the paddles to the heart to start it. Well, guess what? It works the other way too. It can stop it. And the last thing you want to do is die while you're trying to bias your single-ended amplifier. Okay, it's a real downer. So work with one hand to do your clips and keep the other in your pocket. And one last warning before we get started, don't feel obligated to do this, okay? If you're not completely comfortable using a voltmeter, an ohm meter, and working around electrical devices, I don't recommend this. It's not that expensive to get the job done by someone else. Just look at this video as a way to gain an understanding of what the procedure is. But don't try this unless you're really good with electrical devices and with test equipment. Okay, let's drag out the Gretsch 6150 amp and get started. Okay, here's the amp we're going to perform this procedure on. It's a really nice original Gretsch 6150 amp. Okay, I've turned it around and this one still has the original Valco gray power cord and plug. I left that because of the originality of this amplifier. We can see here we've got our 5Y3, 6V6, and 12AX7 tubes like the schematic led us to expect. We've got the original fuse still here in the little envelope. So let's pull this back door and get started on checking our plate current and bias. Step one, this amp is not plugged in. It has not been plugged in several weeks. But just to play it safe, I'm going to connect the end of a jumper cable, one end to the chassis and the other end to a 100 ohm 10 watt resistor. I'm then going to, without touching any metal, go in and touch the other end of the resistor to the lugs of the electrolytic capacitor and hold on each for 10 seconds to allow them to fully discharge. I use this big ballast resistor so that the discharge will be slow and controlled rather than an arc, which can scare you and damage components. Now that it's completely discharged and I know it's safe, I can proceed. Also, I will follow this discharging procedure every single time that I plug the amp in and turn it on and then turn it off. Before I put my hands in the chassis, I will discharge the electrolytic capacitors. Next step, locate the cathode bias resistor. In this case, it's 330 ohms, which is orange, brown, and it's a 1 watt resistor. And it's right out here in front, which is real convenient. Connect your ohm meter across it. One lead on either side. Polarity doesn't matter. We're going to very accurately measure what its true resistance is. Well, true to form, and largely because it's a carbon resistor, it's gone from 330 up to 357.8 ohms. Now I'm going to write that number down on a piece of paper. The actual measurement of the bias resistor, 357.8 ohms. Now, leaving my test leads in exactly the same position, I'm going to change my meter over to DC volts, and then I'm going to plug in the amplifier to a current limiting device. If you don't have one, you better make one. You really need it. It can protect the amp and protect you. I'm going to plug into it. Okay, and now I'm going to turn on the amp and measure the voltage drop in volts across that resistor. Now the volts are going to jump around for a while. Let the amp warm up and let this number stabilize. Okay, it's settled down to about 14.84 volts, which I've written down on my paper. Now I turn off the amp, unplug it from the voltage limiter, and then discharge the filter capacitors again before continuing. You'll notice that at no time while the amplifier is on do I ever have my hands inside the chassis. I do all my connections and everything with it off and with the capacitors discharged. Then I turn it on and do my test. Next, I see that the plate of the 6V6 is pin 3. So I connect my red lead to pin 3 of the 6V6 and the other lead to ground. Before doing this, I make sure that the amp is turned off, that it's unplugged, and that the filter capacitors are drained. Now I'm going to find out what the plate voltage is. I set my meter to volts, plug in the amp, turn it on, and watch while the voltage stabilizes. Looks like it's pretty well stabilized at 296 plate volts, which I'll write down on my sheet. Turn off the amp, unplug it from the current limiter, drain the filter capacitors. Okay, let's review the math. Now, I know that a lot of you hate math, but it's unavoidable in this procedure. Bias resistor actually measured not 330 ohms as we were told, but 357.8 ohms. The voltage drop across the resistor was 14.84 volts. Now you watched as I did this. You saw how these numbers were derived. Now we simply grab our calculator and divide 14.84, which is the voltage, divided by the resistance, 357.8 ohms, and we get 0.0415 amps. Or we can move the decimal 3 places to the right, 1, 2, 3, and that's 41.5 milliamps, which seems rather high for a 6V6, but that is not the critical assessment. We need to keep going. The plate voltage we found was 296 volts. You saw how I did that. Now I'm going to multiply that 296 volts times 0.0415, which was the plate current in amps, and I end up with 12.1 watts. This is the plate dissipation. This is the most critical measurement that you can make on your tube. This tells how hot the tube is going to be, how much heat it's going to give off in watts. The plate current seemed to be rather high. If you look up 6V6s in the book, the maximum plate current is probably lower than this. That's really not the issue. What the issue is, am I going to burn up my tubes? 12 is about the maximum comfortable plate dissipation for 6V6. So this amplifier right now is biased right at the maximum. So it was what we would say biased rather hot, so it has lots of clean headroom. Okay, then we found that the plate current was 41.5 milliamps. For reasons that are a little complicated, I will tell you that the method we used, where we measured the voltage drop across the cathode bias resistor, this method gives you a little bit higher plate current than what is true. The truth of the matter is it's probably more like 39 or 39.5. But I like this method because it's safe, and it gives you a little bit of protection in that it gives you a slightly higher value so that you don't overbias your tube. So as it stands, the tube bias of this 6V6 is that it's running at 41.5 milliamps with a plate dissipation of 12 watts. To me, the plate dissipation and bias are about the same thing. Okay, now this is maximum for a 6V6. In this particular case, I like this amp to be able to be operated at fairly high volume without distortion. So I have plenty of headroom. I have rather a hot bias. If I wanted it to start breaking up, or if I sold this amp to someone who wanted more distortion, what I could do then would be to go in here and instead of the 357.8 ohm bias resistor, I would install, say, a 400 or maybe a 450. I would reduce the bias. I would lower the plate dissipation down to more like 9 or 10, in which case then the headroom would be reduced and the amp would tend to break up at lower volume. I hope that all makes sense. Well, that about does it for today's video discussing the basics of tube biasing. We checked the bias of a cathode-biased 6v6 tube in a Gretsch amplifier. In the future, depending on the response I get to this video, I may cover biasing amps that have two output tubes in push-pull, and also those that are grid biased, which are, I warn you, more complex. So I hope this was interesting and informative, and that you will stay tuned for future videos. Perhaps subscribe to my channel if you haven't already. But no matter what, be careful, be safe, and be back. I'll see you in the near future. Bye for now.